Okay, in this video, we're going to continue our discussion of Lecture 2, Descriptive Statistics, but we're going to focus on measures of variability. So unlike measures of central tendency, where we learn about the centermost score, now we're interested in how do the scores vary or spread from that measure of central tendency. Because you could have a group of scores that are tightly clustered around the center score, or you could have a group of scores that vary quite wildly. And it would be important to know what kind of situation you're dealing with in that particular thing. So there's a couple of measures that we can calculate, and in class we'll talk about some of the reasons for them, for the differences. But one of them is very simple. Range, you essentially take the highest score and you subtract from it the lowest score. And it's going to have some advantages in that it's very simple to calculate, but it's very crude, right? It's a very crude measure, and only takes into account the two extreme scores, so it's sensitive to those extreme scores. Instead, we often focus on two measures of variability, the variance and, more importantly, the standard deviation. And the standard deviation has a lot of special properties, as we will explore as this course moves on. So we focus a lot on the standard deviation. Today I'm just going to sort of focus on the variance, and I'll explain why here in just a second as I walk you through some of the terminology here. So as you can see, for the variance, I've listed two different formulas. Now, this was not true the mean. If you're calculating the mean of the population, the formula is the same as the mean for a particular sample, but it's not true for the variance, because the variance will vary, will be different a little bit in the population as it will be in a sample. And in effect, if you notice the difference in these formulas, not knowing what these symbols mean, the only difference here is, let me highlight this. The only difference is this n-1 in the denominator. Well, I can't really highlight it very well, but you can see right there that this n-1 is the only difference, and that's the correct for sampling variation. There's a little bit of bias because we're not measuring every person in the population when we sample, and so this n-1 corrects for that. Everything else is the same, but we do have some different terminology. You'll notice that we use lowercase sigma squared here to represent variance of the population. And if we're dealing with the sample, we're going to use s squared. So s squared represents the sample variance formula. And so they're different formulas, but same quantity calculated on a population or calculated on a sample. So that's the first thing. And you'll see the same thing is true for the standard deviation. And notice that the standard deviation is merely the square root of the variance. So everything is the same except you have this square root symbol. So the last thing you would do is take the square root of it. And so it's just sigma, or it's just s in our notation, because once you calculate the variance, you just take the square root of it and you have the standard deviation, right? So that's how they're related. The other thing, there are different formulas that I'll sort of give you in class that are based on the deviation score. So remember, in the properties of the mean, we talked about taking the individual score and subtracting from it the mean. Well, there's some formulas that you can calculate variance, and you can kind of see how that works. This formula, though, it's called a raw score formula, not a deviation score formula. And the reason it's more valuable to use is if you have a mean and you make a mistake on the mean, that means all of your calculations after that are going to be impacted by this error in your mean. You'll also notice that if your mean is not a whole number, like if it's 4.7385, it gets really tedious to calculate this kind of formula. And we'll do a couple examples in class so you can sort of see that in action. Instead, the raw score formula, this formula, is a lot easier to use and easier to calculate in those circumstances. So I'd recommend doing that. And that's what we'll do in our example here as I walk you through this particular formula. So we're going to deal particularly with the sample almost always. So I'm going to focus on the sample formula. But be advised that, like, if you did have a population, you have access to the population scores, you would use this formula, which is very similar. The only difference is this denominator there. So what I'm going to do is, like, let's see if I can push this over to the side a little bit so we still have the formula, and then let's look at or consider a situation where we have our data set. We're going to use our sample data set, and we're going to calculate the variance. So we need a couple of things. Let's start with the simple thing. We need n. So the n, just like with the with our mean, is the number of scores. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 scores. So we know that n, if I can draw here, n is going to be equal to 10. 10 scores. That's pretty terrible, but you get the picture, right? 10 scores. So the n minus 1, of course, would be none. So then you'll notice we have this other thing here. And again, the formula is telling you what to do, right? So in this case, you're adding up, you're summing up, but you're not summing up x, you're summing up x squared. So that means that we need x squared. I didn't realize this would be so hard. X squared. So that means that we have to square each one of those numbers and then add them up. So, you know, we have 11 squared is 121. 8 squared is 64. Then we have 36. This is rough. 25. Oops. Maybe you can see that that's 25. This is going to be the same thing. 25. Maybe I'll get better at this as we go on. And then, of course, we have 9, 9, 9, 4, and 1. And so if we add all these up, let me go ahead and add these up. So I'm going to add 121 to 64, 36, to 25. So then we have 9, 3 times. Should get 303. So this value, 303, is sum of x squared. Okay. Now notice this other entity here. The formula is telling us to sum x first, then square it. So that means that we have to add these numbers up and get a value. So just like we did with the mean. So when we add these up, it should be the same as what we had before for our mean formula. So we have 47. Just checking that, make sure that's right. So 47 is sum of x, right? So that means this value of sum of x, that is pretty terrible. X squared is 47 squared, or 2,209. 2209. So once we have these values, you just substitute them in. So s squared is equal, right, to sum of x squared. Well, that would be this 303 number. 303 minus 2209 divided by n, which in this case n is 10. Right? And that's all over n minus 1, or 10 minus 1, which is 9. So now it's just a matter of reducing, right? So you do 2209 divided by 10. Of course, that's going to be like, you can use a calculator, or you could just move the decimal place. What you're going to do, .9. Okay, divided by 9. That would be our next step, right? And then for solving this, you're going to subtract the top two numbers there, or 303 minus 220.9, and you're going to get 82.1 divided by 9. And so your final answer is going to be equal to 9.12, and it's repeating, so you can just put that line up over there. That would be our variance. Now, if you want the standard deviation, you take the square root of that. So S is the square root of this. It's all the same, so you just take the square root of that, and your standard deviation is going to be 3. Just one click for me, 3.020. And really 3 decimal places is adequate for the calculations that we make. You can round to that last third decimal place, although don't round until you're all done at the very end. You don't want to round up here too much because it'll introduce a little bit of distortion. But that's how you calculate the variance and standard deviation. A couple problems in Canvas, so you can check it out. We'll also do some in class.